Today we're going to be looking at bagging, and the first thing we're going to do is we're going to load in the recidivism data that we've seen before that attempts to predict whether someone's going to be arrested upon release from prison within a year. So we've got our data, and I've put it in the form that the classify command wants, which is it wants a list of rules from the features, the input variables, to the class, the answer. And that's a simple matter of just taking most of the data, rule, and then the last piece of the data. And I've only put those columns in it that I want, and I stuck the dependent variable, the whether they're arrested in last. And we've got 430
All right,
pieces
so
of data.
neural networks.
So I'm going to break this up into
the
training
oldest
and testing
of machine
data
learning
in a
techniques,
conventional way.
and
We'll
it is
train our
there are a
classifiers
lot of
using the
different
training
kinds
data,
of
and then we'll
neural
see how they
networks.
perform
This
when
one's
they
called
confront
a
situations they may not have seen before,
neural
the testing
network, and
data.
it has its
So the way I'm going to do
origins
this
and
is I'm going
understanding
to
as how the
take
human
a
brain
random
works,
sample
that there are neurons
of
that
numbers
provide
from
signals
1 to
and those
432.
signals
So I'm going to take all
reactivate
the numbers
other
from 1 to
neurons, which in turn combine to
432,
get more
and I'm going to
neurons.
take 2/3 of them. I feel like
Magically get
2/3
thought out
today.
of that, and I am not
And
enough
make that
biologist
the
to have any
training
idea whether
data.
that's
Right?
accurate
So we'll do that,
representation of how the human
and
brain
we
works,
will
but
then
still networks.
test
So I'm
it.
gonna be
Oh, I'm sorry, we'll
using
create the testing data
Mathematica
by
to
just taking the set
demonstrate
complement of
this. And
all the
idea
numbers
here
with the
is
training
that
data.
one starts
so,
with some
having learned
piece
from
of
my
data,
calamity of
okay?
whenever it was,
So
2 days
here's
ago
maybe
or so,
in this
I
model
want to
we
make
have
sure
3
that
features.
the training
And
indices
we
plus
then
the testing indices are the
combine
same as the
those
length of the
3
data.
features in some
they are.
sort of
All right, so we're all
affine
set up now, and now all we want to do
Basically a
is to
linear
make
combination
some
of these features.
bags
We
out
might
of the
add
training
a
data. And
constant
all a bag
term
is
at some
is
point,
a
and
um,
those produce more features.
we take our
And
data
then
and we just
do
pick
another-
random pieces
we-
of it.
we
And the only
take
trick to it is you
the,
can pick the same piece of data more than once. It gets weighted
Let's
more
take
than
this
once.
value here.
In fact,
We're going to
some
take
percentage
the
of the data, it's
sum
like
of
30%
some
of
weight
the
times
data
this value plus
will
some
be
weight
in
times this
there
value
more
plus
than
some weight
once.
times this value.
And so each
And
bag has
then we're
different
going
sets
to
of data.
take that
It's confronting
overall sum
different
and
types of
squash
data.
it.
And the
So that
idea
it
is to
some
come
value
up
between
with classifiers
0 and
that
1.
confront different
So
sets
we've
of
got the
data and to see
combination
how they
of an
perform.
affine
So I'm going to make
transformation
5
and
bags
transformation,
here,
basically.
and each bag will have
Squashing.
about
You've seen
288
squashing
pieces
functions.
of data.
Basically, the CDF
With
of
me so far?
any
All right.
probability
And in some
distribution
sense, from a
is
conceptual
squashing
point of view,
function.
we're almost done.
Whatever value you
Right.
put in.
The
it
only
says, well,
other
cumulative
tricks I have up
probability
my
of that is
sleeves are
somewhere between
that
0 and 1.
I am
And so
tough on crime,
sometimes you'll
and
actually
therefore,
see
when
probability
we
functions used here. You might see the normal distribution.
I'm sorry, let's see, when we
Distribution involving
um,
hyperbolic
keep someone in
variance that-
prison
but it's-
who would in fact be
In any
arrested,
event, the
that we
idea
get 2
is
points
that
for
one
that.
takes
Whereas
these,
if we
what are called hidden
let
nodes.
someone
Hidden
stay in
because
prison
all the user
when they
sees is
would
they
commit
see
a
these
crime,
features,
I
and they see
gotta
the
own- let's
final
see.
class that
Better do
actually
this right.
results in the real world.
Let me
That's
say it
the user
again and
data.
hope I did it correctly.
And we
Not perfect.
create these hidden layers.
If I
of
predict
data,
you
which
would be
create,
arrested,
as I said, by this sort of
and therefore I
combination
don't
of
let you
take
out.
the data, add it up, squash
And
it,
you were
and
arrested?
then
How could
basically
that
do it
possibly be?
again. Have another
Hold
layer
on a second.
where we take the results of this first
The concept
layer,
is
add
I
them
want
up,
to keep people who are going to commit
squash them,
crimes in
and
prison.
then do it a final time
Um,
with a final
And
squash.
a 1
to
is a
make
prediction that
as
you
to
will
whether
commit
something's
a
going to be
crime.
a 0 or a 1, or how close to 0 or 1
I got it.
it's going
Okay.
to be.
Sorry.
And so
If
that,
you did
the
commit a
only-
crime,
the trick involved here
and my
is you have to know
prediction
what
method
weights
says you
to
will commit a
attach
crime,
to each
that
of
gets me 2
these
points.
connections. So,
whereas
for
if you
example,
didn't
this was
commit a
6 and this
crime,
was
and my
4 and
prediction
this was
method
2,
says you won't commit a crime,
that might
that
give
gets
you
me
at
1
the
point.
end a
This
very
is all a
bad
game,
prediction of what
What's
this
that?
value
Okay.
is going to
Okay.
be.
Right,
Whereas if
we're
this were
assuming that the
-2,
people are in
this were
there
-1,
for having done
and this
something,
were
which is not
-3,
correct. Yes.
that
Could you
might
do,
give
like,
you a
negative
much
points for
better
being wrong?
prediction. not
Yes,
just
you
on this particular
could.
basis. But
You could. I just set that at 0.
See
We
what
could do it.
cumulative
We could set this up as a
error
punishment
is.
scheme or a reward
Um,
scheme, and I'm going to get
and
rewards
so-
because it's a utility
Good,
function.
good.
Right, so there's my
notice
recidivism.
seems
And now what we're
simple.
going to do is we're going to take all of our bags, and for each bag, we're going to classify that bag using our easy naive Bayes classifier. And I've got to tell it that variables 2, 3, 4, and 6, which are race, work experience, marital status, and educational status, are nominal variables. Otherwise, it may get confused. And so what we should end up with is one classifier that's been trained on each bag. Okay, so let's do that. Okay, we did it. Now, what I'm going to do is extend this idea. I'm going to use the same code, but for each bag, I'm going to train it on 1, 2, 3, 4, 5 methods. We're going to train it for a naive Bayes classifier, a random forest, a support vector machine, a neural network, and nearest neighbors. Okay? So we should end up with an array of classifiers. Neural nets are slow, so it's going to take a little while. And all right, there we are. So we now have our multiple classifiers. And if I look at the dimensions of the multiple classifiers, I'm going to see it's 5 by 5. 5 classifiers on 5 bags. Probably I should have 7 bags so it's not confusing, but you'll live with this. All right. I'm now going to show you a fancy thing that you haven't seen before, and that in fact I've never used before. It's a new feature of Mathematica 10, which is how to create a report using a template notebook. Okay, ultimately we're going to create a document, a notebook, for each of these 5 classifiers, saying how'd I do when you bagged me. Okay, let's see how we do that. We're going to create something called an association object. Association objects are very simple. They're just instead of having the expression having numbered parts, you know how you can extract the pieces of a mathematical expression? Like if I write 2, 3, 4, 5, and I want to get the third part of that, I just go like that, right? Or I could say, what is part 2, 3, 4, 5? What's the third part? Okay? But an association, sometimes this R is very association oriented. Sometimes you don't want to remember it's the third part or the second part. You want it to have a name. And so associations let you have named parts. So I'm going to say, look, here's the training data. It's the data of all the training indices. Here's the testing data. It's the data with all the testing indices. Here are the classifiers. Don't worry about why I have to make it input form of some list of classifiers. And here's a classifier type. It's a classifier string. So just to show you how this works, supposing I have, I let A be an association, and let's see, height is 70, and weight is 150, and vision is 2070. Okay? If I want to get, there we go. So we have our association. If I want to get the weight of this person, I just go A and I go weight. Okay? So it's acting here almost like a function. The association is acting like a function. I'm calling the weight thing and it's coming out as 150. Or if I want to get the height, I just do this. Okay? For those of you who've seen in other languages, these are sometimes called hash maps or maps. What else are they called? Associative arrays. It's all the same thing. It's a way of relating data to a name. Okay? And so that's all I've created. I'm creating a function here that creates an association object. Okay? So now what all I have to do let's look at what this little piece of, first of all, let's evaluate this function. And let's evaluate this. All this has done is to create lots of associations. So if I say, let me take the third one of these, it's saying, here's your training data, here's your testing data, here's the secret information about your classifier. Notice it's got all this glop in it, which is why we don't print it out usually. That's the information that it has, okay? And what I'm now going to do is to say ship this information over using this generate document function and use this template, okay? What's the template? Let's look at it. Bagging report, okay? How did I create this template? Instead of saying file new notebook, I said file new template notebook, right? And it's really easy to use this. Suppose it's like a fill in the blank thing. So if I say, let's actually create one of these. Here's my little association. Okay, I'm going to create a new template notebook, and I'm going to say you just do it like a regular notebook. This is a notebook, okay, and we'll make this the title. And now we'll say report on person. Okay. And we'll say, at this point, we want an expression. And we're going to say, well, actually, not yet. The sum of, we're just making text here, just like we're writing a report, of his height and weight is. I have no idea why you would ever want to notice the sum of those two values, but they do. Okay? I make an expression, and here I'm just going to write a regular mathematical expression, and the only trick is, instead of writing height plus weight, I'm going to say it's a named thing, and I want the height plus the weight. Oops, not there. The weight. They put the quotes around it. All right, and now we're done. That's my template notebook. I'll save it as class template. Okay, here's all I have to do to make my report. To make my report, I'm going to say generate document. This is just a path, and instead of saying bagging report.nb, I'm going to say class template.nb. And A is just fine. That's what this association is. And so now if I execute this, I get a report. I get a new notebook, and it has the information in it. You'll notice it's printed out 220 twice. That's annoying. And now I can edit my report. Let's get rid of that. Let's go edit my class template and tell it evaluate but hide the input. And it gives you a little icon which is somehow supposed to represent hiding. And now, when I run this same thing, see, I get a report. So this is very useful. It means that you sort of generate, it's almost as if your notebook becomes a function. This whole template notebook is kind of like a function that gets applied to an association that you've created that has your data in it. And so you can use this, as I'm about to show you, to do pretty cool things. So we're about to generate a document that uses this template and that uses this association as it's all of them that have been created. So we should create the N5 documents. And this will actually take a few moments. There's one. There's 2, 3, 4, 5. Okay, so let's look what they have to say. Let's look at our bagging report, okay? And let's make it bigger. What do we learn about bagging? All right, when we use the classifiers on the training data, we got error rates of, depending on which bag we got, of anywhere from 29% up to about 36%. When we saw how did that work on the testing data, again, we ranged, depending on what bag we picked, from 25% up to about 35%. And you can see here the confusion matrices on each of the bags. We can see how each of our classifiers did on the various bags. But when we bagged it, meaning basically the classifiers vote, okay? They each have their own system, and they vote, and whatever the majority vote is, that's the class. Okay? Bagging works with voting. And so our bagged classifier ended up at 29.8%, which is better than most of these. Okay? And so it made a slight improvement in the quality of the prediction. Yes.
So 5 bags, each of the 5 bags makes a vote? Or?
They each vote, and so if 3 of them voted for 0 and 2 of them voted for 1, it's recorded as a 0.
So, but because I don't see this number correspond with any one of the 5, so how does that voting take place?
Okay, so we end up with the bagging procedure with multiple classifiers. We ended up here with 5 classifiers. Each of those classifiers is, in this example, a naive Bayes classifier. Each of those classifiers, each of those 5 classifiers is capable of making a prediction on each piece of data. And so if 4 of the classifiers say this person is going to be arrested, and 1 of the classifiers says no, he's not, the bagged classifier says he's going to be arrested. And so in some sense, what you're doing is you're introducing variation in the data that this algorithm confronts, and then kind of taking the modal response of this algorithm to these different pieces of data, which are similar but not identical. And the idea is one hopes you produce a pretty robust classifier that won't get it massively wrong when it confronts new data. Right? So that's bagging, and it's, you know, the virtue of bagging is it's really simple, I think, to understand. It's just you take slightly different data, you develop your classifiers, and then your classifiers vote. Okay? And that's bagging. And this simple method sometimes produces improvements. Okay? The underlying classifier doesn't have to be a naive Bayes classifier. Here, the base classifier, the underlying classifier, is a random forest. One thing you can see is the random forest actually did better on the training data, but when we tried to extrapolate it to the testing data, it didn't do so well. It fell down. Whereas our little naive Bayes, it didn't fall down too much. We've got our confusion matrices, and our bagged classifier is a 0.32, which is actually, on the testing data, which is actually better than any of the base classifiers. So bagging with a random forest here did seem to help a little bit. Okay, and we can do the same thing for support vector machines. Support vector machines, they're all over the place, aren't they? How'd they do when we bagged them? 0.25. So I would say our support vector machine did pretty well. That is, now the performance on the testing data looks like the performance on the training data, rather than having this risk of having numbers like 0.35 and 0.319. And we could go through the rest as well, but I'm going to spare you that. Okay? But that's what I wanted to teach you there, was the concept of bagging, this report generating facility if you ever wanted to use it, and that's basically what I'm hoping you got out of it. Okay, so you can build your own bagger. Bagging. Save. And we can get rid of that. We can get rid of that. We can get rid of our bagging report. All right, let's go to stacking. Okay. Let me see if I can explain stacking in English. Stacking is kind of cool, except that in my experience it doesn't work. But sometimes it does. There are 50 academic papers showing that stacking could work. The idea is, again, we have a committee of classifiers. The classifiers do not have to be all of the same type. Okay? They must, you might have a naive Bayes and a support vector machine and a neural net, etc. They all work on the training data and develop their models. So let's say we had, let's actually just walk through. Okay, let's walk it through. Let's load up. I'm going to give myself a clean kernel again so I have nothing up my sleeve. We load in our recidivism data and we process it as before. All right. And I am going to stack 4 classifiers here: a support vector machine, a naive Bayes, a nearest neighbors, and a logistic regression. And we're going to do our training and testing data just as before. We're going to use the same utility function as before. All right. I'm now going to produce diverse classifiers. That is, I'm going to produce one support vector machine classifier, one trained naive Bayes, one trained nearest neighbors, and one trained logistic regression. This is the same code as basically we used before. Okay? Let's see how they did. And let's magnify this so it's a little easier to see. All right, so they all performed somewhat similarly. Looks like our support vector machine did best, naive Bayes and nearest neighbors did worst, and logistic regression did okay. But one thing is, you might not know ex ante which of those classifiers is going to work best. And of course, in my little simple problem where we only have 400 pieces of data, it's really pretty easy to figure it out. You just run all of them and see which seems to be doing better. But if I've got 1 million pieces of data and 100 variables, that might start to get inconvenient. So one thing we might want to see is, are there ways that we could combine the wisdom? This is sort of like a jury, where you have different perspectives being brought to bear. All right, so here's our confusion matrix plot. I'm not sure what we're going to get out of that. There it is. Let's go to the next key piece of code, which is, for each classifier, I want to see how they predict the training data will perform. So I'm going to map each. I have all of my classifiers, my 4 classifiers. I'm going to map those over the training data. So if I do that, what you'll see, if I look at the dimensions of this, is I get 4 rows of 288 columns. In other words, it's saying, okay, the first row is, how did my support vector machine do? And the second row is, how did my, Bayes do, etc. Okay? What I want to do is, I now want to flip that data on its side. I want to transpose it. So instead of having 4 rows of 288 columns, I have 288 rows of 4 columns. Because that's the kind of data that I can then use to run another classification. So that's what this transpose is doing here. And now all I want to do is to say, what's the right answer, okay? Here's the first piece of data. This is the prediction of the first classifier. This is the prediction of the second classifier. This is the prediction of the third classifier. This is the prediction of the fourth classifier, and this is the right answer. That's why it's called supervised learning, is the supervisor knows the truth. Here's the second piece of data. Here's what the first classifier said. Here's what the second classifier said. Here's what the third classifier said. Here's what the fourth classifier said. And here's the truth. So in this one, only this guy got it right. And we do that for all 288 pieces of training data. Okay? So if you look at the form of this data, which is deliberate on my part, you could see, hey, we could actually use machine learning on this. Not on the original data, but on a transform of the data. Okay? And in this respect, it's a little bit like a neural net. Remember what a neural net does? The neural net, you have your original data, you have your affine functions and your squashing function, which produces new data. You apply affine functions and squashing functions to that, you get a new layer, and at the end you're done. Okay? So stacking has that flavor to it, where you're taking the original data, transforming it by base classifiers, and then running one final classifier on that. And you could, just with neural nets, you can have, in theory, you could have 27 hidden layers. We could do yet more stacks where we run 4 different classifiers on this, and those make predictions, or 7 different classifiers. In my experience, what it turns out is, given how good most of our classifiers are these days, you sort of run out, you've exhausted the possibility. If you're using a decent classifier to begin with, I don't find much that stacking, even though it's cool, it doesn't actually get us very far. But let's see. Our final classifier, I'm just going to use logistic regression, which is you know what that is. It's a simple classification method. So let's run it. And now, let's see how we did. We're going to test our stacked classifier. Right, that's not good. We run that. We run this on our testing data. And let's see. This is the actual function, by the way, if you ever want to see this is what the actual sort of function inside the logistic regression thing. Let's see how we did. 25.6% error on our stack, and our original classifiers were getting errors of 25.6, 29. So in some sense, it looks to me like it said, the support vector machine's the best guy. I'm going with him. And I'm betting, could be wrong, let's just see if I can figure this out. I'm not sure if I can interpret what this means, if that in fact is what it's doing. It might be what it's doing. But in any event, what you now have is the concept of stacking. And all you need to do to make a stack is you select an array of base classifiers. They could all be the same, and just start them with different seeds and see how the different seeds do. And then use some sort of meta-learning algorithm, which doesn't have to be a logistic regression. I could have used naive Bayes on the stack and come up with a second level of prediction. Okay, that's stacking. Boosting. Okay. Do I want to save this? No. Boosting is, I think, the hardest one to understand. So that's a negative. The positive for boosting is it might actually work. That is, I've seen examples where boosting seemed to make a significant difference. There's a whole bunch of theoretical literature about why does it work and does it really work, etc. But I've seen instances where it does work. All right, so let me see if I can explain. And by boosting, there are a zillion flavors of boosting. But let me see if I can explain to you in English again how boosting works. So we run a simple classifier. And again, one of the virtues of boosting is it can be fast. We run a simple classifier. We see how it does. For the values that it got right, in the future, we're going to decrease the weight of that data. That was easy, so we're going to decrease the weight of that data. For the ones that it got wrong, we're going to increase the weight of that data. Okay? And now, we're going to run the same classification algorithm, whatever it is, on the weighted data. So the one trick is that your classification algorithm needs to be able to handle weighted data. Okay? If, like Mathematica at present, it cannot handle weighted data, Classify cannot handle weighted data, you can sidestep this by, instead of putting weights on the data, to basically use a bagging method where you pick items out of your set of data based on the weight. So you're going to have duplicates. The points that you are weighting heavily, you may see 5 times, whereas the point that you downgraded, you may not see at all. So it's not exactly the same, but it's the same idea, which is, okay, some of the stuff we know how to do. Maybe it's really far from the border. It's not hard to classify, okay? If, you know, the mushroom is bright red and it smells awful and it has it's obviously poisonous, don't eat it. Whereas if it's, you know, in the store, okay, it's probably not poisonous, you can eat it. Those are easy. The hard one is the mushroom that doesn't smell, but it is kind of funny looking in the gills, etc. So we're going to heavily emphasize the problem cases. We'll run our method again, and we'll see how we did. And for the third round, we'll adjust our weights based on how we did this time. And at the end, the idea is you kind of weight each of these classifiers so that you minimize the total error. It's kind of an iterative process where you're creating a sequence of classifiers. And in some flavors of boosting, at the end, you have weighted classifier voting. Okay? So that's the idea behind boosting. Is it worth my going through? I actually tried to build a simple, let's do a simple booster. Okay. Here's my simple booster. Here's my true function. This is what I'm going to use to generate the data. It's some complicated, I think it's a complicated function. Maybe it's not that complicated, but I think it's a complicated function of 5 variables. And now I'm going to create the data. There's the data. So here are random values. The first 1, 2, 3, 4, 5 are the features, and the last thing is the class. Okay, so there it is. How many did I make? I made 100 of them. All right. And now I'm going to use, as my machine learning algorithm, I'm just going to use a logistic model. I'm not going to do anything fancy at all. I'm going to use the simplest thing, which is good old logistic regression. Right? So I run logistic regression on it with the existing weights, and it is going to come up with what are the residuals. And the bigger the residual is, that is, the wronger it got, that's weighted more heavily. And that the new weight counts for 50%, and the old weight counts for 50%. So we're sort of gradually adjusting the weights, and there's this whole art form to how you do this weighting, or other ways of doing it. But this is what the pros do. This is cheap and dirty boosting, right? So now what we'll do is we will come up with, we start all the weights as being equal. Everybody's equal. Now we run new weights, and you can see that now this point is a 1.13, and this point maybe was really easy. It's a 0.69. And so what I can do is I can just do this a lot of times. I can use the Mathematica's nest list command to keep generating new weights. So I do that. We're done. And this is one of the virtues, it's pretty fast. And right, what did I do here? This is a slightly more elaborate version. This is my bootstrapping version, where I'm going to use a Bayes classifier, a naive Bayes classifier, and instead of, since it can't handle weighted data, I'm doing that sampling thing where we pick the problem cases more frequently. Again, I'm going to run this system here, and there's some fancy stuff going on here. And I end up with the sequence of classifiers. Okay? I end up with a sequence of 10 classifiers. Here's the first one that I ran. Here's the final one that I ran. And we can see, I'll generate some new data and see how we do on the new data. And my first classifier that I ran, it had an error of 0.29. The last one I ran had an error of 0.29. And so my cheap and dirty boosting didn't accomplish anything. Okay?
Do you think it'd be better though, just because every time you run the test, it seems like
It should get better.
it would be more significant? I
Yeah,
guess,
the problem is that as I'm
right.
here's the issue. The problem is that as I'm weighting the problem cases, now the ones that I got right before turn into new problem cases because I.
So it doesn't just remember, I guess.
Well,
that
it
looks
this
like
is
that?
this is my cheap and dirty classifier
Oh,
that I built
so
doesn't.
there's
The
a-
real one does, and so this may simply be an artifact of my not spending enough time with cheap and dirty boosting to get it to work properly. But yes,
Are there demonstrations to see non-cheap
Yes.
and clean?
Yep. Funny you should mention that. Right, let's turn now to the non-cheap and dirty methods of doing this meta learning. Thank you, Brittany. All right, so let's actually knit this RMD file. Oh, and I made it a PDF, which I don't want. I want it to be a slidey thing. All right, let's do it again. Let's turn it into a slidey presentation. Knit. Okay, so this one I'm going to use the famous IRIS data set. I finally resorted to using IRIS. You've seen it, right? It's like the petal length and the sepal length, and then you have to see is it a setosa or a versicolor or a virginica or something. There are 3 kinds of irises in the world. All right, so I'm going to make my training data. This is how you do it in R. And here's our testing data. It's all the data that isn't training data. And it's 100 cases of 5 variables. And my testing data, why is it 50 by 5 and not 2/3 by 5, not 67 by 5? All right, I'm going to ignore that problem for the moment. We make a little formula. I want it to predict the species of flower based on everything in the data. That's what that little dot means there. So I don't have to write out everything. It just says take everything and use it to predict. All right, let's do our base classifiers. Let's see how our base classifiers do without all this fancy stuff. I'm going to run a J48 decision tree on it. And it gets, it does real well. J48 gets 91% kappa, which is really good. And what is it? It's getting 94% correct. So even before I get to all the fancy stuff, I'm doing pretty well. Right? But let's do something really rinky-dink. Let's do a decision stump. A decision stump is basically pick one feature of the flower and figure out which is the best classifier. You only get to pick one thing. So maybe if its sepal width is greater than 7, it's a virginica or something. Okay? And when I do that, irises aren't that hard. I get a kappa statistic of 0.46 and I get 62% right. All right? So what interests people is in situations like this where you've got something simple, a decision stump, can you use boosting to make it really good? And where you have something that's pretty darn good to begin with, J48, in some circumstances, 94% is pretty good. If we're classifying poisonous mushrooms, really 94% is not very good. Okay? So can we use boosting to be a lot more certain that the mushroom that I just picked is okay? All right. So in Weka, the way we do it is we have to set up the base classifier. We have to tell it, okay, when you're doing this boosting, use this base classifier, and this is the code to do it. Okay, this is just saying here's the classifier to use, and here are some options with it. You don't need to worry about those options. Here's a really simple one. Just use decision stump with the base options. Don't fiddle with anything. Just use the out-of-the-box decision stump system. And I've called those J48 ops and DS ops. All right. So here's what we're going to do. We're going to use a variant of boosting called Ada Boost, which is like the most famous booster of all. And here's our code. Use Ada Boost 1. Here's our formula. Use our iris training data. And here's the base classifier. Use a J48. So when it does that, it really took no time at all. Here's what you get out. This looks like one of your basic Weka classifier objects. How'd we do? Okay, and what you can see is we actually didn't do as well as when we had just the base J48. We're still getting 92% right, and our cap is 87%, but that's actually worse than we did before. Okay, so this boosting may not accomplish very much where you're doing pretty well before. But let's look at good old decision stump, which you remember was at 62% accuracy. What did we get? %98 accuracy. 0.969. Yes.
Isn't an issue with boosting is if you don't know if it's good or bad, that if you're trying to apply it to an unknown set of
Yeah,
data,
you'd have to do some preliminary testing with it, seeing how well you're doing. If you're not doing well, it might be that boosting would help you. Might be. Okay. So that's pretty cool. Okay. Boosting, and this is what there's like this whole boosting intellectual lobby that loves boosting. This is what this is their exhibit A. Look, we took the world's simplest classifier, it doesn't take any computer time, and with a little bit of boosting, we turned it into a great classifier. Bagging. How does bagging do? Well, bagging, look what we got. I bagged my J48s. I got 100% right. Darn impressive. I bagged my decision stumps. Didn't help. Okay. Stacking. Here's how you stack in Weka. It's all the same code. This was like the world's easiest notebook for me to make because all I did is write it once and then I just cut and paste, and change the word bagging to stacking. Okay. And so how did we do? We did horribly. We got 40% right when we stacked. That's not very impressive. How do we do on our stack decision stump? Do I believe this? I guess I believe this. It did terribly. And look what it's doing. It's saying everything is a setosa. Everything is a setosa. So, I'm going to raise this possibility, shocking as it might be. I wonder if there's a bug in Weka's stacking. I don't see how it could be that terrible, especially for a J48. All right, something to think about.
could it just be that that's an easy way to get the right answer some of the time? So it's kind of like a lazy student just writing B on every multiple choice.
Yeah,
Well,
yeah.
that was easy.
Yeah. I don't know. I don't have an answer for you on that. I'll tell you, in poking around this stuff, I find weird things like the Mathematica neural net thing doesn't seem to work very well some of the time, and then some of the time it works great. So I haven't figured this out. And this is all. This is why, if I were, there's not a lot of case law on it, using machine learning in a courtroom setting, in a litigation setting. If I were a good judge, I would be very careful, and because the results here, we can get wildly disparate results. And so if you need to manipulate something, if you need an answer, if you fiddle with enough machine learning algorithms, you will probably get what you want. And so when you're cross-examining a machine learning guy, you've got to find out how many things they fiddled with that aren't in there, that didn't make their way into the report. Because there could be a lot of bodies buried there. And that's basically what I have for you on machine learning. You now know more than most people do about machine learning. I guess I could say a few more things. Okay, all we've talked about so far is unsupervised learning. I'm sorry, all we've talked about so far is supervised learning. And by supervised, we mean that somebody knows the right answer. There's a class at the end, okay? Unsupervised learning is we're not trying to predict the class. we're trying instead to, usually it's to form clusters, to say that these things kind of go together and these other things kind of go together. And it's sometimes useful because once you know that something falls within a cluster, you may be able to make predictions about what the behavior will be, or at least you'll be able to say it's a similar phenomenon. So, for example, Netflix might use clustering. There's no right answer as to whether this is a good movie or not. But they found in the past that people who like Gone with the Wind also might like Casablanca or something. And therefore, if you've only watched Gone with the Wind, it's got other things in that cluster. Okay? Or Pandora, okay, or Spotify or any of those things, they're using clustering algorithms that, you know, you've picked whatever, some jazz artist from the 40s, and so they know that there are other artists who are similar that you might like. And so all these recommendation systems that we see are really based on this concept of unsupervised learning. Weka has lots of support for unsupervised learning if you ever find yourself actually needing to do it, to do clustering. Mathematica has a command called find clusters, and it has various methods that you can use attached to it, and it will also do a pretty decent job, actually a very good job, of finding clusters. One thing, just like supervised machine learning, kind of what you get out of it depends very much often on what the details of what algorithm you're using. So too with clustering. Clustering can be very fragile, and so one person might consider, I don't know, I'm going to have to use classical music because that's the only thing I know about. They might consider Mozart to be, well, they wouldn't really, but let me come up with a better bad example. Hold on.
Tchaikovsky, Mozart.
They might consider Tchaikovsky and Mozart to be in two different clusters, whereas maybe another one would say, well, they're both orchestral, they use lots of notes, they're melodic, and so they're in the same cluster. Okay? And maybe they would put Bach and Mozart in a different cluster because Bach is a little more spare in the use of notes than some Tchaikovsky was, or less orchestral.
I read a paper about someone do it for MBA positions.
Okay.
So it's like they classify different positions based on like what type of, I don't know, a bunch of different variables like that.
Right, and so, I mean, clustering is a very common thing. You can cluster law schools based on attributes, you can cluster anything. And I think, even though we haven't covered it, that if you have a clustering issue, your experience using RWeka will let you figure out how to do clustering, and your experience with the rest of Mathematica will let you feel pretty comfortable doing clustering. So, anyone have questions? Okay. Well, I will be very thoughtful and let you out early. Do feel encouraged to come, ask me for any assistance that would be useful for either the homework or the midterm that's next week. And as I think I mentioned, the midterm is basically it's not comprehensive. I'm just going to pick a certain area and ask you about it. So hopefully you did study that particular area. So it's a little high risk. And it's problem based. That is, I'm going to give you a deposition transcript and some data. And there's a lunch break in the deposition, after which you're supposed to come back and have maybe done some data analysis yourself and have some questions for the expert based on either things that the expert said earlier that are kind of strange, or that in light of the data analysis that you've done maybe aren't as certain as the
be taking the exam?
So that's a very good question. I take it that this is not the most comfortable environment.
Exactly.
All right. So my job is going to be to find you a room in which to take the exam. We might do it in the Healthful Library if I can shut that down for an hour and a half, and if not, hopefully I will find some place for you to take it.
I know you'll give us data files, but can we also have things on paper? too?
You can use any.
Like,
You can have anything you want.
I mean,
It's an open book.
but will you give us a printout as well? Because I like to highlight.
Oh, you want a printout?
Well, I mean, I know you'll give us like a PDF.
Yeah.
data
Yeah, with being
But-
time limited and only having one computer screen.
Yeah.
I gotcha. Okay, that makes sense.
Or
All
can we
right.
have 2 computer screens? Can you find
Can I bring my monitor?
a thing?
Can I bring my extra computer?
Yeah, like, bring your extra
I'll bring my
monitors.
monitor.
No, we're gonna have one. Everyone gets one computer. That seems
But what
fair.
Can I bring
about
my
a
monitor?
You want a big monitor?
Okay.
My monitor's so small, it's so much easier when I plug it into my big
You
one
get
at
to
home.
Like in a
monitors?
classroom, we can just.
Well, you could.
Like, can I just bring my TV?
Oh, seriously? I just have it like sitting there. And
So, yes. Okay. If you can get it to work,
awesome.
great. And I understand your point about a printout. Well, I'll give you a printout of the deposition transcript and the content of the question.
What is the outlet situation? Just, I guess, if people are bringing
I'll bring
monitors,
a monitor.
they need to.
I have no idea, so that's why I would
Yeah.
check it out before you hook up. All right.
Bring some extension cords.
Yeah, I'll be the one
Search
for
for
monitor
checkers.
extension cord.
I brought my monitor for your con law final. For
Yes.
Codex.
Can you also give us like answers to the problem set 4 to 6? I don't know if it's already.
4 is 4 not? They're up. They're done.
Oh, like
They're
5
done.
to 6.
Oh, it's up there.
Oh yeah.
Yes.
5 and 6 on
Okay, hold on. Those are done. So I think we could dispense with recording the remainder of this session. Bye bye.